Alright, so let's take a look at the assignment sheet because things have changed, you know, since we're gonna do the worksheets.
Is it a positive change?
Yeah, you get less work.
Oh. Is it dated that has to move back?
So instead of doing all the star problems, we're only doing selected star problems. These are all the same problems from the book now. So here, where are we today? November 1st. So tonight, gradient 6, you're gonna find that this is the toughest part of the chapter right here. Gradient 7, gradient 8. Next week Monday, no class. Next week Tuesday, yeah, that's an extended study for test. And then the test can be next week Thursday, right before the holiday.
Oh wait, I'm not gonna be here next week Thursday.
Okay, take it Wednesday then.
Oh, okay.
We got another trip?
Yes, cross country.
Yeah.
Cross country?
Yeah.
Nationals, yeah.
Regional.
Regionals.
The team can compete in regionals?
Yeah.
Oh, you guys competed last year?
No, we got invited this year.
Oh, you have to be invited.
It's like separate from like LH or like
Yeah,
states.
Because you guys won 3 in a row, then they said, oh, they must be pretty good.
Yeah, and then we went to the one earlier in the season in Arizona and did well enough, I guess.
You get a 2 for sure.
And then look, I wrote answers on the bottom too, so you don't have to like flip to the back of the book anymore. But these, again, just like the old worksheets, these are the answers I got from the
No.
other periods, so some of them may be wrong. Oh, so before we start, when I was driving to school, or was it when I was driving home yesterday, I was actually thinking about, you know, the path of steepest ascent, and remember that thing? I said we need to worry about it. But now that I thought about it, we need to worry about it.
No!
Yes. So here, so pay attention, Joe. So let's look at give me a graph, give me an equation of a graph that kind of looks like a mountain. Z equals,
X squared plus Y squared.
Okay, so that's a paraboloid, but it's opening upward, right? We want it like a mountain.
Negative.
Root x squared plus y squared.
No, this is it. So you guys know what a paraboloid is, right? So you minus it, so the thing is opening down. Now let's shift it up. Okay, let me just put 4 then, or what's this? Whatever number, 1. Okay, so would you agree that the paraboloid looks like this then? X, Y, Z, woo, like that. It shifted 4 units up. The z-intercept is 4. So let's say you're standing on a point, standing at a point on the paraboloid right there. Give me a coordinate of a point. Joe, that lies on this paraboloid.
2, 1, 1, 2. Oh, 1, 2.
1, 1, 2. Okay, we'll go with that one. So what is the path of steepest ascent? Well, it's pretty obvious, well, since it's symmetric here, don't you just aim straight for the tip of the paraboloid? Since it's symmetric, but lots of times it's not symmetric, yeah, so what do? Well, what did it say in the homework about the path of steepest ascent? It's in the direction of the gradient, but see, what we were doing yesterday is we were looking at the 3-dimensional gradient. What you're supposed to do is you're supposed to look at the 2-dimensional gradient. So, if you think of this as f, what is the gradient of f here? Park.
Negative 2x. Negative 2y.
Okay. So at this point right here, so basically you're only looking at the x and the y coordinates. What is the gradient at this point? Plug in 1 for x and 1 for y, and you get
Negative 2.
-2, -2. So here, it's probably easier if we think about it from the top view. So here, from the top view, so we have a paraboloid going like this, yeah, going like that. So like, this is where it intersects the xy plane, and then it comes up like this. So kind of like, right? These are the contour plots like that. So at the point 1, 1, 2, like right here, I don't know, let's just say That's the point 1, 1, 2. What is the path of steepest ascent? Here's the gradient. The gradient has an x component of -2 and a y component of -2. And here, let's put it further out like this. So doesn't the vector look like that? In the xy plane? So that's where you would aim to get the path of steepest ascent. That makes sense, yeah? Because see how you're headed for the apex of the paraboloid?
Is the path of steepest descent a straight line?
No, the path is not going to be a straight line because it's a paraboloid. You're going to be going like this, right? You're going to be going like that. It's a curve, yeah. But that's the direction, and every time you change your position, you're going to have a different vector, yeah?
So that would just be like the derivative at
The gradient.
Yes.
The gradient, yeah. So like, what if you had something that's not symmetric? What if you had like, okay, can you think of a mountain coming up like this? Oh, I don't know. It's not symmetric. So if you're standing here, the path of steepest ascent, now depending on the terrain of the mountain, so at this point, you compute the two-dimensional gradient, and then at that point, the vector points like that. That's the direction you should walk if you want to get the path of steepest ascent. Yeah.
What does the gradient shoot towards, or like?
It's the steepest ascent. Like if you want to climb the mountain as fast as possible, then you follow this path. But every time you get to a new point, you're going to get a new vector. It's like over here, since it's symmetric, it's going to be the same all the way. But if you have something that's not symmetric, like when you get here, maybe the path of steepest ascent now, then you got to go that way.
Oh, okay.
And then maybe at that point, then it's going to be that way. So it changes, right? The gradient is going to change at every single point, yeah?
But why would that be steeper?
Well, this is just like, because what, like, I can't even think of a shape that's like not even symmetric. Like here, something like this, the mountain looks like, you draw a side view of the mountain. Like that. So like if you're here at the bottom, you compute the two-dimensional gradient, the path of steepest ascent would be like, maybe the vector would be, now remember, it's a two-dimensional thing, yeah? So it points like that, right? Let's say this is the xy plane. So that means if you're standing on the mountain, you see the vector pointing that way, that's the way you should walk. Yeah? It's a two-dimensional vector, that's why. But then, so let's say you walk that way, but then you're actually climbing up the mountain.
Yeah.
You know what I mean? But you're looking at the two-dimensional vector, maybe it's projected on, maybe you can see it somehow, yeah? So when you get to this point, then you compute the two-dimensional gradient. Now maybe it points, I guess it's hard to tell from this, but yeah, like I said, then you look down, maybe it points that way a little bit. So then that's the direction you walk. That's the path of steepest ascent. And then the steepest descent would be just in the negative direction, yeah? So for example, if you're standing here and you want to descend as quickly as possible, then you go the opposite direction of that vector, you go that way. So that's what they mean by the gradient is the path of steepest ascent. It's a two-dimensional, because if you think of the three-dimensional one, then it really doesn't make sense.
Okay.
Okay, now last night's homework, look, so this is the problem on the worksheet. Why don't, did you have, now these are exactly the same problems for the book except selected ones. So, Jason Wang, did I notice that number 1A was, you had a question on?
Oh, wait, what?
Right,
I thought that was our homework, right?
Yeah, that was the homework.
Oh, okay.
That was the way it happened.
These are the same problems, I just hand wrote them.
Yeah.
This was like 20-something years
That's
ago,
the right
I wrote it.
Can you do that because I couldn't?
Which one, number 1?
Number one.
Yeah,
Number
I didn't
one.
get number.
Okay, let's do number 1 then. No, did I do this one yesterday? There was something I did yesterday. X cubed plus y cubed equals 3xyz at the point 1, 2, 3 halves. So the first thing you do is you make one side 0, correct?
Correct the window.
Okay, and then you think of this as your function of 3 variables. Then you compute the three-dimensional gradient, which is, okay, Wang, what is the x, the partial with respect to x? 3x squared,
Minus 3y.
okay? Ha? Y component?
3y squared minus 3x.
And Cho, the Z component?
Negative 3xy.
-3xy. Okay, correct. At this point, what is the gradient? If I plug in 1 for x, 2 for y, and 3 halves for z, did you guys already do this?
Negative 6, 15 over 2, negative 6.
Say that again, negative
6,
6,
15 over 2,
15 over 2.
negative 6.
Everybody agree?
Yeah.
Okay, so this vector is perpendicular to the tangent plane. So like, whatever the surface looks like out of this three-dimensional surface, at this point, here's the tangent plane. This vector is perpendicular to that tangent plane. But that's what you need to write an equation of the plane. So the equation of the plane is simply negative 6x plus 15 halves y minus 6z plus d equals 0. And then you simply plug in that point to figure out what d is. And then simplify the equation. Yeah.
Okay, wait, that's not what the answer said.
Wait,
Well, let's do it. Yeah, there's no way that could be the answer, yeah? I don't know, that's why. That's what, I just copied it down.
no, in the book it says that too.
Yeah,
Ascent to the back.
yeah.
Well, let's just compute this. What happens if I plug in negative 6 plus 15 minus 9
You get 0.
plus d equals 0? D is 0, so if this is 0, how do you simplify this? What's the fastest way to simplify this equation? Multiply both sides by
Divided by 3.
2/3. 2/3? So you get negative 4x plus 5y minus 4z equals 0. There you go.
Because it isn't.
Does it have to be
That is the answer.
I didn't.
Here's part. Do you have to simplify?
Yeah.
No, everything is optional. Yeah, I'm gonna take off 1 point for not simplifying. Who in their right minds needs coefficients as fractions?
Students.
That's okay, -1. 99 is a darn good score, right? About that. That's not the answer.
Number 17, please.
Is that on there? Look up there. Let's just, okay, people, let's just worry about these, because these are the ones that are gonna be on the test. Because when I write the test, it kind of comes from these problems here, you know. How about number 2 then? Find the points where the tangent plane is horizontal. That means the x and the y components gotta be 0, yeah? Didn't we do one like that yesterday?
Is that? Oh, I think that's number 21.
Number 21 is which one?
Is number 2.
2. Do we need to do it?
Is equals xy?
xy plus a cubed over x plus b cubed over y. No need to do those.
Sure.
Okay, let's do it.
Which one? 2? A or B? And don't say both. 'Cause you can do one, you can do them all.
Let's do
2,
B.
B. I don't know which one in the book this is. Z equals xy plus a cubed over x plus b cubed. Does that say b cubed? Let me take a look. Yeah. So now, if we want to find where the tangent plane, again, so like, if you have like a three-dimensional surface, if the tangent line is going to be, tangent plane is horizontal, then we need a vector that points like straight up or straight down, right? In the positive z or the negative z direction, which means the x and the y components of the gradient got to be 0. So, is it necessary to make one side 0 in this problem?
No.
No, you really don't need to, but if you want to, you can. Because you're not going to look at the z component anyway, right? You know what I'm talking about?
Yeah.
Okay, so here's f. So the gradient is, okay, partial with respect to x. Who's got this one? Part.
Y plus.
Me.
Oh, wait, sorry. Y minus a cubed over x squared.
Okay, component with respect to y, pa.
X minus B cubed over y squared.
And then with respect to z, that's too easy, -1. So we need the x and the y components to be 0. So y minus a cubed over x squared gotta equal 0, and x minus b cubed over y squared gotta equal 0. So we gotta work with these equations. So y gotta equal a cubed over x squared, x is equal to b cubed over y squared. And what do you think I'm gonna do with these? We have to find the points on this graph.
So.
You
plug
plug it
down.
in. Now,
Yeah.
you gotta find a way to plug it in so that you can solve it, right?
Plug the X in.
So, what shall we do? I'm trying to look here. What would make it nice? Okay, here. So z is equal to x, y. Yeah, why don't we just change everything to x's then? Yeah? So what happens, okay, so xy, a cubed over x squared plus a cubed over x plus b cubed over y which is a cubed over x. Oh, but wait a minute. Wait a doggone minute. What about the z though? Okay, let's just see what let's see what I don't know. Let's just see what happens. So what do you get here? A cubed over x plus a cubed over x plus x squared b cubed all over a cubed. That's what the z coordinate is. No, you know what? I'm doing the wrong thing. We need to solve these equations right here. These are the equations we gotta. So how can we solve those equations?
Solve for x.
Solve for x in this equation and plug it in here. Yeah, let's do that. Okay, pay no attention to what I did there. That's stupidness. So y equal a cubed over x squared. So what is this squared? B to the 6 over y to the 4th. Is that correct? Did I do that correctly?
Yes.
Yeah.
So y is equal to a cubed y to the 4th all over b to the 6. Now how do we solve for y?
Divide both sides by one.
No, then you lose the solution y equals 0. Oh, but y cannot be 0. So we can divide both sides by y. You gotta be careful when you do that now.
I knew that. And
So 1 equal a cubed y cubed over b to the 6. So y cubed is equal to b to the 6 over a cubed. Cube root both sides. Y equal b squared over a. Once you figure that out, where should I go to figure out what x is? Right here. So x is equal to b cubed over that squared, which is b to the 4th over a squared, which is a squared b cubed over b to the 4th, which is a squared over b. Yeah, it's kind of like a nice symmetry there. So the point where that happens is a squared over b, b squared over a, and then how do I find the z coordinate?
plug in
You plug it back into this. Can you guys do that? Yeah, you guys can. Hey, look, it comes out nice. Hey, that's a good problem for the test, I think. Yeah. What the heck was I doing there? That's what happens when you get old. That's why somebody else is going to have to teach you starting next year. You know, Yeleni's actually was thinking of hiring a multivariable calculus teacher last year.
Okay.
Yeah, but I guess the applicants didn't pan out, so then they said wait 1 more year or something.
Oh, because we were in different periods.
No,
They're not gonna make 2 classes to like 3 people. They're not gonna do that. No, they're just not thinking of. Well, a lot of they were thinking of hiring an upper level math teacher, but they said we can wait a little bit longer.
So
Oh,
they'll
okay.
only teach multivariable.
Yeah, teach upper level, but several of the teachers had experience in teaching multivariable calculus. at whatever schools they were at.
So what are all the other periods that
I don't know, calculus, pre-cal, algebra 2.
Is that
Not
what
team
you're
coach.
Is that what you're doing?
you said you didn't want to teach BC. You're ready to teach.
Yeah, you know why? I was thinking about it. It's not really a challenge, that's why.
The A
'Cause-
is a challenge.
Yeah, AB is a challenge. Like BC, pretty much everybody's gonna get 5s, right? Even if you teach them wrong, they probably get 5. No, seriously.
That's true.
They're just, Mr. Park doesn't know what he's talking about.
Last.
They'll probably get 5. Okay, what about 3? Do we have to do 3 and 4?
So now, you wanna like.
Yeah, but who's gonna watch this?
Ah, that's true.
Okay, are we gonna do 3 and 4 or no need? You guys got it.
Is that the same?
Yeah.
Find the angle of intersection.
Oh, he did.
Oh, no, yeah.
No! How do you, okay,
Oh,
think about,
that
we did this before. How do you find the angle?
we
That
can
part.
find the 210.
Yeah.
Let's-
Okay, what the heck, let's just do it anyway. Number 3, you have a curve here, given parametrically 2t. So this is like x equal 2t, y equals 3 over t, z equal negative 2t squared. And the ellipsoid, x squared plus y squared plus 3z squared equal 25. They intersect at the point 2, 3, negative 2. Find the angle of intersection. So we have like an ellipsoid. I'm trying to kind of like that. And then you have this is like a curve that's going to get, and then they intersect at a point like that, and it continues on like that. Right? You guys kind of understanding what's happening? So right at that point, what is the angle of intersection? Well, what does it mean to have an angle of intersection? You have to look at the tangent plane of the ellipsoid. So here, like, let's look at a side view. Here's the ellipsoid. Right at this point, let's say that's the point. Here's the tangent plane. And then you got the curve. The curve is going through that point like that. Okay, that's too steep. Like that, maybe. So how do you find the angle of intersection, of where they intersect? So if you remember, when you have a tangent plane, what do you always look at? The perpendicular vector. And then, right at this point, how do you get the vector that points in the direction of the line like that? Come on, we just did this.
Directional gradient.
No,
In
we
the
did it like last chapter.
In the direction of which line?
Of the path. So this is a path, right? Like right in here. What is the tangent, like the direction? Like that. Or like right there, boom. Or right there, boom. What vector is it? Should I give you multiple choice?
Yeah.
A, position vector. B, the velocity vector. C, the acceleration vector. D, all of the above. E, none of the above.
Can you repeat the question?
E.
If you have a curve, which this is a curve, right? It's a curve in 3 dimensions. At any point, how do you get the tangent vector?
Oh, velocity.
It's the velocity, that's right. Okay, so we figured that out. So we gotta do 2 things. We gotta find the gradient, because the gradient gives us the vector that's perpendicular to the tangent plane, right? Okay, let's do things one at a time. So here is the equation of the ellipsoid. What should I do? Make one side 0, so like this. That 25 is not gonna matter anyway. So that's f. What is the gradient of f? This one's easy. 2x, 2y, 6z. At this particular point, what is the gradient? If I plug in 2 for x, 3 for y, and negative 2 for z, what do you get? 4, 6, negative 12. This vector is perpendicular to the tangent plane. Everybody agree? Because that's what the gradient tells you. It's a vector perpendicular to the tangent plane. So we got this. And then, how do I get, so if here's the curve, how do I get a vector that points in the direction of the curve, or that's tangent to the curve? The velocity vector. So the velocity vector is, Cho?
Wait.
I'll do the first one. 2. If this is the position vector, velocity vector.
Negative t squared.
No,
What? Negative?
negative 2.
What you talking about?
Oh,
I did the first one. The derivative of 2t is 2.
yeah, -2.
That's a 3.
Oh, -3t to the -2.
Okay, I was hoping you'd say negative 3 over t squared, and then
Right.
negative 4t.
Yeah.
Okay, there you go.
It's the same.
Yeah, but Mr. Clark, what number do I plug in for t? Well, you gotta figure it out. Look at this position equation. When it gets to this point, what does t have to be? It's pretty obvious here. T gotta be 1, right? T gotta be 1 in order to get this point here. So what is the velocity vector at that point? Let's write it right here. If I plug in 1 into the velocity vector, what do you get? 2, -3, -4. That's this vector. How do I find the angle between the two vectors?
Dot.
The dot product. Cosine of the angle between two vectors is the dot product, which is A. You guys remember how to find dot product? You multiply the x components, you multiply the y components, you multiply the z components, all over the length of the first vector, which is the square root of 4 squared, I just do it, 16 plus 36 plus 144. And then the length of this other vector, which is the square root of 4 plus 9 plus 16. And I will leave the simplifying to you. And it looks like it comes out to cosine inverse, what is that? 19 root 29 over 203. Sometimes it comes out like that. Yeah, I like that. That would be a good problem for a test. Because then you gotta know things. I like that. And shall we just do number 4 for funsies then?
Yes.
Well, show that the sphere given is tangent to the ellipsoid at the point 2, 1, 1. The answer on the bottom says duh. X plus y squared plus z squared minus 8x minus 8y minus 6z plus 24 is equal to 0. It is tangent to the ellipsoid x squared plus 3y squared plus 2z squared equal 9 at the point 2, 1, 1. So you have a sphere and you have an ellipsoid. This is side view. It's going to be tangent right there at the point 2, 1, 1. You know what? Maybe we don't really have to do this. How would you show that they're tangent at that point? They have the same. Well, they obviously they intersect there, but how do you show that they're
Slope.
actually tangent there? Yeah, but there's no slope in 3 dimensions.
Vector.
They have the same tangent plane,
Okay.
which means they have the same gradient there then, right? So shall we just do it for funsies then? Okay, so this one is already 0. If you think of that as a, what's the gradient of the sphere then? Do it. Partial with respect to x, 2x minus 8. Partial with respect to y, 2y minus 8. Partial with respect to z, 2z minus 6. At this particular point, what is the gradient? If I plug in 2, 1, 1, what do you get for the sphere? Okay, I'll do it. 4 minus 8, 2 minus 8, 2 minus 6. Okay, that's the gradient, right? So all we need to show now is that the gradient for this one is parallel to this, right? Pointing in the same or the opposite direction, doesn't matter the length. Okay, so shall I make one side 0? Okay, I did. So if we think of this as g, what is the gradient of g? Partial with respect to x, 2x. Partial with respect to y, 6y. Partial with respect to z is 4z. And at this particular point, what is the gradient? 4, 6, 4. Are they multiples of each other? Yeah, so therefore, right? Because even though this one is the opposite of it, that just means, so like the gradient for the sphere will point that way, but the gradient for the ellipse is that way. It doesn't matter. Same tangent plane, right? Because it's perpendicular to that plane. Yeah, that was not that. Okay, so like I told you, today's lesson is the toughest lesson.
There's a less.
Maybe it's the best.
Cho, what do you expect?
I
Finish the homework. You guys can have free paper, period. Look, tonight only got 6 problems. I handpicked it from the book. You know what? Why don't we just do one of them from the board, from it, then you only have 5 problems for homework. Yeah. You guys, this is sad. You guys are supposed to be the top students in the school.
Do you still say that's your BC?
That's it. This is the last year. This is the last year I'm teaching this.
Wait, you still say that's your BC class?
What?
Did you say that's your BC class too?
No, the reason why I taught BC again last year, this year, is because since I did all that hard work last year making practice tests and stuff like that. No, for real, I spent so much time doing that. I told Dr. Chin I'll do it one more year.
And then another year.
And then you're not.
And then after that.
But yeah, but now that I have it all, it's like it's really,
Bored.
it's not, yeah, but like I said, I like a challenge. Like AB, it's pretty tough to get them to get 5s on the AP exam.
But they all.
Here, I'll tell you what happened last year. Up until last year, I had 90% 5s
Nine.
Or who got?
For AB.
in AB, which is, I think it's pretty difficult to get that.
That's like a 12% 5 grade or something. It's like really low.
What do you mean, what's low?
The 5 grade.
Oh, like 70, 60 something
Oh,
percent.
shit.
Oh, really?
Is that coffee?
Yeah.
Oh,
Anyway, last year, let's just say the average went down.
by how much?
Because they were terrible last year.
That's.
Well, what did it go down?
Like this year, it seems like they're back to normal. Last year, they were like, I tried every trick in the book. I couldn't motivate them to like, even memorize derivatives.
Oh, that's terrible.
You couldn't do that either.
That's bad.
Well, at least for the AP exam though.
Yeah.
So,
Okay, anyway,
Memorize it for the AP.
let me get a new piece of chalk.
like, kind of.
Hey, did you find that video you mentioned?
Okay, so today, we are actually computing extreme values.
No.
Why, did you read ahead?
Yeah.
Yeah, it's complicated. It's not easy. So in 2 dimensions, how do we compute extreme values? You compute the derivative. You can either do the first derivative test or the second derivative test, yeah? Okay, so what we're gonna do today is, this is like equivalent to the first derivative test. And then tomorrow's lesson is something equivalent to the second derivative test. But it's very complicated. I'll do number 1 for you. Okay, so you got z equals 2x minus x squared minus y squared. You want to graph this on the app and see what it looks like?
Sure.
Okay, after. I don't know, I have no idea what this graph looks like. I'm thinking it's some kind of paraboloid, like I'm looking at the equation, yeah?
Okay.
Oh my goodness. Okay, so here we go. So this is what we do. Like, first thing you gotta do is find where is the tangent plane horizontal, just like last night's homework. So how do we find, so think about it. If you have a surface, this is like from the side view. You have a surface like this. How do you find maximum and minimum points where the tangent plane is gonna be parallel to the xy plane like that, yeah? And then you have possible maximums, okay? So these are like critical points in 2 dimensions, but like what did I say yesterday? In 3 dimensions or higher, we call them
Station.
stationary points. So the stationary point is where the tangent plane is horizontal, parallel to the xy plane. So first step, we need to compute the gradient. You want to let one side equal 0, you don't have to. Because we're only going to look at the x and y components of the gradient, yeah? So if we think of this as f, the gradient of f is equal to, what's the partial with respect to x? 2, how come it says 2x minus 2x? Okay, 2 minus 2x, what's the partial with respect to y? Negative 2y, and the partial with respect to z is negative 1. Okay, but that part we're not going to look at. So, in order for the tangent plane to be horizontal, the perpendicular vector got to point in the positive z or the negative z direction, which means the x component and the y component's got to be 0. So all you got to do, it's pretty mechanical. Set the x component equal to 0, set the y component equal to 0, and just like last night's homework, solve it. But this one is so easy to solve, look. 2x equal to x equal 1. Right? Y equals 0. So at the point 1, 0, what is the z coordinate? 2 minus 1 minus 0 is 1. At this point, there's a possible maximum or minimum point. Now, in two-dimensional calculus, we would make a number line, but how the heck do you make a number line for 3 and higher dimensions? You can't. So this is what we do. Now pay attention because this is the hard part. So you have a graph. I'm trying to, okay, this is the side view again, yeah? Side view. So here's the xy plane down here. Like let's say you compute a stationary point like over there. How do you figure out if it's a max, a min, or neither? So what you do is you compare this point. So here is the point 1, 0, 1. You compare it to points nearby. Actually, we don't need the z coordinate. Let's just look at the x and y coordinate. Okay? So, how do you compare it to points nearby in 3 dimensions? You do this. You compare it to a point. So you down on the xy plane down here. This is the point 1, 0. Oh, what the heck? It doesn't matter. We're going to compare it to a point 1 plus h, 0 plus k. That would be like a point near, very near it, like that. Okay? So, what the heck? Let's put the z coordinate in. What is the z coordinate? 1. And what would the z coordinate here be? If you plug this in, yeah, what the heck? Let's just do it.
2
Plug this
plus
in
2h.
to the thing, you would get
2 plus
2 times 1 plus h, oh, got it, minus 1 plus h squared minus 0 squared. Everybody agree? Now just think, common sense. How do you figure out if this is a max, min, or neither? Now, if this were a maximum point, what would happen if you subtract this, or subtract this from this? In other words, if I subtract f of 1 plus h, 0 plus k, and then I subtract f of 1 comma 0. If I take this and I subtract that, yeah, if it's negative, then wouldn't that be a maximum?
No, you have to do the
If this point minus that point is negative, wouldn't, for all values of h and k now, not just for some values of h and k, then wouldn't that be a maximum point? If I take this and subtract it from that, take this and subtract that, and you get a positive number, then wouldn't that be a minimum point? And then, if it's sometimes positive, sometimes negative, then we don't know.
Wait, how would it be sometimes positive, sometimes negative?
Because depending on the value of h. Okay, so here we go. So let's do that. So let's take this and subtract that.
Oh my god.
Well, actually, we're talking about the z coordinates now. Yeah, that's this. So this thing basically gives you the z coordinate. So it's this z coordinate minus
Oh.
that z coordinate is positive or negative. That's going to tell us. So let's do that. So let's simplify that. Go 2 plus 2h minus 1 minus 2h minus h squared minus 1. So what we have to do is we have to determine, is this quantity always positive, always negative, or we cannot tell. Sometimes it's positive, sometimes it's negative. So let's simplify that. Hey, these cancel out.
It's always a
The 2's cancel out. All you're left with is negative h squared. So it doesn't even matter what the value of h is, right? Because when you square it, it's going to become positive, and then you multiply it by -1, it's going to be negative. So if you can think of h and k as very small positive numbers. Think of it as very small positive numbers. So this number will always be negative, so therefore this point is a local or relative maximum.
You could think of them as small negative numbers too, right? Like it doesn't matter.
Yeah, it doesn't matter, but I think it's easier if you think of it as very tiny positive and just positive numbers. Okay, so this was an easy one. Now, there's certain quantities. Okay, let me ask you this. So everything depends on what this thing comes out to. So let me ask you this. What if it comes out to this, h squared, these are things that are gonna come up tonight, minus 2hk plus k squared. What can you say about that? Well, isn't that the same thing as h minus k quantity squared?
Oh, it's 0. Oh no, it's positive.
Yeah, so it's gonna be positive, right? Because if you have a quantity squared, it's gonna be positive, so therefore you would have a local minimum there, yeah? Okay, what about this? These are two that come up tonight. H squared plus hk plus k squared, and h squared minus hk plus k squared. These two things are gonna come up. When you see this, anybody wanna take a guess?
Wait, what?
Me.
It's in the book, if you bother to read the book, these two things come up. They're both positive, all the time, no matter what. So both of these are positive, which means you would get a local minimum. I think it says something about the proof is beyond the scope of this book, or something. Or maybe they do have a proof there, I'm not sure. Okay, what if you had something like this? What if it came out to this? H squared minus k squared.
Ambiguous.
Yeah, sometimes it's positive and sometimes it's negative, right? So you don't know. So in that case, what's the conclusion then? What if it's sometimes positive, sometimes negative?
It's me.
Yeah, so, well, what's neither then?
Cannot be determined.
No, then you get a saddle point. You remember this thing over here? Like on the hyperbolic parabola, you see this point over here?
Yeah.
See how, if you look at it in this plane, it would be a minimum. But if you take a plane this way, it would be a maximum. So we call that a saddle point or a mini-max.
Oh.
So if it's sometimes positive, sometimes negative, then we call that either a saddle point
Oh.
or a mini-max.
Wait, so it just depends on what plane you're viewing it from?
Yeah,
Oh.
but see, because we're talking about, when we're talking about maxes and mins, we're talking about like compared to points nearby, is this point the highest point on the graph compared to points nearby? Or is it the lowest point, or you cannot tell? So if you can't tell, it's gonna be a saddle point, just like a horse's saddle. There's no way I can draw that on the board. All right, so tonight's homework, it's very mechanical. You take the gradient, set the x and y components equal to 0, solve it, however, and then, is there any trig there? No, there's no trig. I guess I'm saving that for the test then. So sometimes you're gonna have trig there, and then you just gotta solve it. And then you have to test it by doing this. Tomorrow, we're gonna learn another way to test it, because sometimes the algebra gets very involved over here, that's why. We call it like the second partials test. It's kind of like the second derivative test.
That's
All right.
the first
Wait, what
partials
about-
test then?
I don't know what they call this. I guess, yeah, you could call it the first partials test. Yeah,
What about Lagrange multiplier?
that's not until the next chapter, I think.
Isn't that finding maximum in?
Oh, that's 2 sections from now. Yeah, that's not, don't worry about that. Don't worry about that. Yeah, but I believe that's finding maxes and mins with side conditions though, isn't it?
Oh.
Yeah, that's not what we're doing here. So don't worry about that yet. Just worry about this. Okay, so you only have 5 problems to do for homework. I'm just warning you though, these don't have any trig in it, but on the test, I put a good trig one on there.
Wait, how you?
Like have sines and cosines, tangents, whatever.
Oh, come
Okay, just sines and cosines there.
on. Well, Mr. Park, I watched Taken on Sunday.
The what?
I watched Taken.